When you think of something being continuous, you think of it changing very slowly, very smooth. And so we're going to start with a provisional definition of what it means for a function to be continuous. A continuous function is one whose graph can be drawn without lifting your pen from the paper. So, for example, if I have a graph like this, you could imagine that we could start down here and you could draw the graph in one continuous motion here, and this would be continuous. While something like this, if we tried to draw the graph, when we would get to this part right here, we would see that we would need to lift the pen off the paper in order to get down here and to continue the graph. This is not continuous. So there are three ways in which a function can fail to be continuous. First, we could have something like this. We have a graph that has a piece missing. It could maybe be defined to be something else here or just not defined at all. That's called a removable discontinuity. It's removable because you could imagine if we just plugged the hole right here, then we would have a nice, smooth, continuous function. Here we have something that's a little worse than removable. It's actually something where the graph jumps from one place to another. And so we call that a jump discontinuity. And finally, we have the worst case scenario. That's where the graph just kind of explodes here. We have an asymptote. This is called an infinite discontinuity. Okay, so now it's time for the actual definition of continuity. Let f be a function and c is a real number. Then f is continuous at c if the limit as x approaches c of f of x equals f of c. So in order for the function to be continuous at c, three things have to hold here. We have to have f of c defined, and we also have to have the limit as x approaches c of f of x that has to exist. And finally, the limit as x approaches c of f of x has to equal f of c. So let's look at the example we had earlier. We can see that we have something that's a problem here. There's a jump discontinuity when x is 1. Okay, so let's check the three conditions. F of c must be defined. Well, we see that f of 1 here is defined. If I look at f of 1 is 1, so that works. Okay, no problems there. The limit as x approaches c of f of x must exist. Well, here we have a problem. The left-hand limit as x approaches 1 is 3. The right-hand limit as x approaches 1 is 1. Since these are not the same, the limit overall does not exist. And so we can see that this function is not continuous at x equal to 1. Let's look at another example. So here are the three conditions, and here is the graph of another function, and let's look at places where we have discontinuities. So first off, if we tried to draw the graph, we would get to a point here at x equals -3 where we would need to pick up the pen from the paper in order to get from the lower part here to this upper part. So we can see that we have a jump discontinuity. That's where the jumps from one place to another. And that's at x equaling -3, right over here. Okay, so that's one discontinuity that we have. And we can also think of it in terms of the definition. We can see here f of c must be defined, while f of -3 is defined, but the limit does not exist. We can see that we have a left-hand limit that's different from a right-hand limit. Okay, so now we keep going, and then we see we have an asymptote here. So that is an infinite discontinuity. So I have an infinite discontinuity, and this infinite discontinuity is at x equaling -1. And again, let's look at the definition of continuity. F of c must be defined. Well, here we have a problem. F of -1 is not even defined. So we're already in trouble here. So we can see that this is another place where we have a discontinuity. Okay, then we keep going, and it looks like right here something strange happens. Looks like the graph kind of changes. It maybe is a piecewise function. But is it continuous here? Well, let's look at x equals 1. F of 1 is defined, and the limit as x approaches 1 does appear to exist. The left and right-hand limits both exist and are equal. And it looks like the limit as x approaches 1 of f of x does equal f of 1. So in this case, yeah, it's continuous here. And you can tell also we don't have to pick the pen up off the paper in order to draw this part of the graph. But then right here we have another problem. This is a removable discontinuity. That's where we just have one little piece missing. And that's a removable discontinuity at x equaling 2. And again, we'll look at the definition here and see how that works. F of c must be defined. F of 2 is, well, f of 2 is not defined. So that's a problem right there. So we can see we do have a discontinuity at x equals 2. All right, we'll look at one more example here. Here is a piecewise function, f of x equaling e to the x if x is less than 0, and this rational function, x squared minus 2x minus 3, all divided by x minus 3 if x is greater than or equal to 0. Now I want to figure out where the points of discontinuity are. So if we have a piecewise function, one thing we should look at is where it switches from one type of function to another, and that would be at x equals 0. So e to the 0, what's that? Well, anything to the 0 power is 1. And then how about if I plug in 0 for the other part? So I get 0 squared minus 2 times 0 minus 3 over 0 minus 3, and that ends up being negative 3 over negative 3, which is 1. So I can see that at 0, these two graphs kind of link up in a sense. If you were to look at the graph, you would see that they both match up at 1. So we do not have a discontinuity at 1. Okay. Well, e to the x, we know, is not going to have any strange things happening. That's just a nice graph without any removable discontinuities or asymptotes, vertical asymptotes. So that one is not going to be a problem. But what about this thing here? Let's see if that factors. So let's rewrite this here. We have x squared minus 2x minus 3 over x minus 3, and does the top part factor? And it does indeed factor as x plus 1 and x minus 3. Okay, great. And then I still have an x minus 3 down here. And I can cancel out the x minus 3's, and this is the same thing as x plus 1 as long as x does not equal 3. So let's see here. What happens when x does equal 3? Well, then we have a removable discontinuity. This graph is going to look like the line x plus 1, but at x equaling 3, there's going to be a hole. So we have a removable discontinuity at x equals 3. Okay. Let's look at this up here. Check these three conditions. F of 3 must be defined. Is f of 3 defined? So if I were to say what f of 3 is, I would look at this part of the function because 3 is greater than or equal to 0. And when I plug 3 in here, I end up dividing by 0. So no, it is not defined. So already we have a problem here with the first condition. Therefore, the function cannot be continuous at x equals 3. And that's what we saw right here.